In our last video, we looked at Newton's law of universal gravitation outside of planets. Now let's take a look at Newton's law of universal gravitation inside planets. So suppose you are able to drill a giant hole into a planet and move inside of it such that now some of the mass of the planet, continue using here, some of this mass of the planet here has been removed and it's now above your head. This planet is now pulling up on you. Well, this pull upward, so let's do your belly button here, this pull upward here on you by this mass that's by your left ear is going to counter the pull down from this giant swath, let's call it Australia, over here. The tiny mass close at hand is going to produce the same amount of pull as the giant mass far away, because remember, Newton's law of universal gravitation, force of gravitational attraction, is an inverse square law. So when you move twice as far away, that's going to result in a pull that's 1/4 as big. Because if you make r twice as big, r squared, there's going to be a factor of 4 there. So now the pull is 1/4 as big because we've doubled the distance. Well, that would mean that in order to get the same pull, we need to have 4 times as much mass. Hence, we get a small mass up here of this dirt that's been removed from the hole, and now it's sitting on top of the surface of this planet. That small mass is going to roughly balance this guy. And that same is going to be true in the other direction. From this small mass pulling upward is going to cancel this giant mass over here. And the result is you can draw an imaginary bubble around your, and I've drawn it around your feet. Technically, it should be around your belly button. But you can draw an imaginary bubble in which the only mass that doesn't get canceled out is that which is still underneath your feet. So the farther into a planet that you go, there is less and less mass of the planet still under your feet, and more mass of the planet that's outside that's going to cancel out. So all of this stuff outside, all of this swath out here is dirt and magma and the mantle, the inner core, the outer core, all of this, the different sections of the planet. And as the farther you go, more and more is removed from having a gravitational effect on you. Now, naturally, at this point, we're ignoring pressure, the crushing pressure, and heat, and all that other stuff. We're just pretending that we have a uniform planet here that's just uniform dirt and rock all the way through. So we're not worrying about that part right now. All we're looking at is the gravitational effects of moving inside a planet, and the result is we're going to enclose, so this is you, and then this is the planet, P for planet. But as we go into the planet, we are going to enclose inside our imaginary bubble only a certain amount of dirt that's centered on the center of the planet and only extends as far out as where am I standing right now. This doesn't seem to be done all that often gravitationally, but this is of great importance when we start talking about electricity and electric charges. Dealing with this sort of idea where you have an extended charge, a charge that takes up a certain amount of space, and then you move inside the charge. You have to be able to deal with that mathematically. And the mathematics for that and the mathematics for this are the same math. So let's start and introduce the math with gravity and dirt and a planet that we can see, so that then we can, by analogy, move over to electric charges that we can't see. So when you're moving inside the planet, and you're enclosing less and less and less of the mass, but you're also enclosing less and less of the volume. And as long as the planet is of uniform density, this forms a nice, neat ratio that is constant. So if planet, and the same thing is true for electric charges. If you're dealing with an electric charge that is of uniform density all the way throughout, and then you move inside of it, that ratio of electric charge through the space stays the same, as long as it's uniform. if the planet is uniform density, then you get this ratio. The Greek letter rho looks like a P, but it's not a P, it's the Greek letter R. Rho is going to be the mass of the planet divided by the volume of the planet. And if it's uniform, then it doesn't matter how much of the planet I'm enclosing. This is sort of like if you've talked about in chemistry or general science, homogeneous mixtures. So like, say, salt water. You take some water, you take some salt, you dump the salt in the water, and you stir it up. And now it doesn't matter if you scoop out from the top or you scoop out from the bottom, you're going to get the same salt water content. As opposed to, say, chocolate chip cookies, where you mix in the chocolate chips, and if you take your spoon and you scoop out a scoop from the one side and you scoop out from the other side, you're not guaranteed to get the same amount of chocolate chips in the mixture of the cookie dough. In this case, with uniform density, it doesn't matter where I'm taking from the planet, I'm going to get the same ratio of how much mass have I enclosed inside my imaginary bubble versus how big is that bubble. Now, we're only going to deal with spherical planets. We're assuming that all planets are spherical, which means that the volume of the planet is going to be the volume of a ball, 4/3 pi r cubed. Now, let's take a look at what happens to this equation that we have for Newton's law of universal gravitation, the force of attraction between you and the planet. It's going to change because we're not going to let your mass change, but we are going to change the mass of the planet. So force of gravitational attraction minus g mass enclosed of the planet, mass of u over r squared, and we don't care about the r hat right now because we already know that's radial vector, and that just deals with direction. We don't care about the direction right now. So the mass enclosed, it's very hard to figure out how much mass did I enclose of the planet here. So what I need to know is I need to know how much mass total there is, and I need to know how much volume total there is of the planet. Those are a lot easier to figure out than this guy. So what we're going to do is we're going to set up proportionality as I have here and rearrange it so that mass enclosed is all by itself. Because these two guys are things that I would know, and then that would be my variable. Mass total over the volume total of a planet of radius r would be 4/3 pi r cubed, and that's going to be big R because that would be the total radius of the planet. And then we have the equivalent ratio over here, 4/3 pi little r cubed, and that little r is our variable because what I'm doing is I'm diving into the planet. How much? Well, we'll find out when we get there. Things that are the same cancel each other out on either side of the equal sign. And what we have now is an expression that will let us get rid of the thing that we can't know directly and replace it by things that we can measure, which are such as the size of the whole planet, the radius of the whole planet, and how far am I standing from the center right now. So let's take these guys and substitute them into mass enclosed up there and see what happens to our equation. So force of gravity minus g m total r cubed over big R cubed mass u over r squared. Now notice we have a little r squared in the bottom. That's part of our original equation. And a little r cubed, that's because we're diving into the planet. And these guys are going to partially cancel each other out. So let's clean this up. All of those guys are constants. If I gave you numbers, you would plug the numbers into there. And then our one remaining variable is r. So we have an r cubed here and an r squared in the denominator. They cancel. We're left with just an r in the numerator, which I've written off to the side. Now, if you remember from math class, if we're going to graph this, here's my variable. Here's a bunch of numbers that we multiply and divide together, and we just get one overall number. And then here's my answer. Well, if I'm going to graph this from math class, here's y. All of that junk together is slope, and this guy turns into x. So what I have here now is a linear relationship in terms of how heavy am I going to feel. Remember, the force of attraction between the planet and you is going to give an indication of how heavy do you feel. And it's not exactly the case. We've already discussed that with the normal force and standing on the scale in an elevator, and the fact that you will feel a different weight depending on how the elevator is pushing you. But that depends on how much is the planet pulling on you in the first place. So this guy tells you that the farther that I get from the center of the planet, that's little r, the heavier I'm going to feel, because this guy gets bigger, the whole thing gets bigger. That's opposed to, well, suppose I'm outside the planet, like we are right now. We're outside the planet. We're not, in a cave or something with a mountain over our heads. Well, let's go back to our original equation. If I'm outside the planet, we've enclosed all the mass of the planet. We have our mass. And now we're going to divide by how far am I from the center of the planet squared. So if I get into a rocket ship and I move away, I'm not enclosing. So here's the boundary of the planet. And then outside of this is empty space. If I move away from the center of the planet, I'm increasing the distance that I am from the planet's center. But I'm not going to be including any extra mass because there's nothing out here. So if I, become an astronaut and I'm up here floating in the space station, here you go, an astronaut, and I'm a distance, we'll still use r, from the center of the planet, all of this up here is empty space. There's nothing here. So this is a universal constant of like the whole universe as far as we can tell. This is a constant of the planet. This is a constant of you. You're not going to change mass much in the rocket ship. Even if you throw up, you're not losing much mass. This is the guy that's the variable. So when we make a graph of this, and we'll come back to making a graph for the next example where we have a non-uniform density planet. So we have R, the big R, and we have the force of attraction between them. And we're making this a negative graph because since it's attractive, it's going to be a negative force. This says we have a linear relationship between the center of the planet and the surface of the planet. So if we graph that, and the slope of that graph would boil down to big G times mass of the planet times mass of you divided by the radius of the planet cubed, because remember, this is a three-dimensional object, so that r cubed goes with the 3 dimensions. But then once we get to the surface of the planet, if you jump off the planet, meaning you get into a rocket ship and you leave, now it's an inverse square, but it's still negative. So inverse square goes like that. And I'm going to draw an arrow there to indicate that it doesn't matter how far to the right you draw your r variable, your r axis, it's just going to keep approaching 0 very slowly. And the way we indicate that we have linear and inverse square here is we draw f is proportional to r, and f is proportional to 1 over r squared. Where this fishy symbol, Greek letter alpha, is proportional to. So the one variable f is proportional to at r until you get to the surface of the planet, and then the force is now proportional to the inverse of r squared. Now that's for a uniform planet where you can set up a ratio, and this ratio is constant whether we're talking about the whole planet, the whole mass with the whole volume, or just part of the planet with part of the volume. What if it's a variable? What if it changes? Well, if it changes, then what we're dealing with is a planet that has a non-uniform density. So let's move over and let's take a look at a planet that has a non-uniform density. I've drawn here a planet, and right outside here in the rim, that's the outside of the planet. And this is a solid planet. It's solid all the way through. but it's a different solid as we go through. Instead of just being uniform, the same kind of rock all the way through, it's going to change so that it gets more dense the closer to the surface you get. So at the center, there's almost nothing. And then at the outside, that's where most of the mass is. So what that means is this skinny little ring here of radius r and thickness dr. So think of a balloon, and you're blowing up a balloon. So when you're blowing up a balloon, the film of the balloon material itself, there we go. The film of the balloon material itself, it has a thickness. It's very, very thin. So since it's very, very thin, we're going to use dr, because if you take a step from that inside ring to the outside ring, you've made a very, very tiny step, but it was still a step. There is still a thickness there. And we're going to have to deal with a situation where mass enclosed over volume enclosed is not constant. What we have instead is it's equal to this expression. So rho, let me do it this way. Instead of being constant and equal to total over total, it's now going to be equal to some function of the radius from the center of the planet. Now, in order to find the mass enclosed, remember over here, what I wanted to do was I started with this equation, and I wanted to get rid of mass enclosed and replace it by stuff that I know. And I did that by setting up my ratio here. Now, I'm not going to be able to set up a ratio. What I'm going to have to do is I'm going to have to set it equal to the function. So as I rearrange this, and this is volume, rho is equal to, mass enclosed is equal to rho times volume enclosed. And this is always going to be true. It's just a question of what kind of density am I talking about here? And I've given you the equation for this. In real life, I'm not sure that geologists can really get this specific most of the time. But for our purposes, let's run with this. Otherwise, we can't do a mathematical analysis here. So instead of rho, we're going to put in kr squared, where k is just some number. And instead of volume, we're still dealing with a sphere. This is, I've drawn circles here because two-dimensional surface, but it's a sphere. And the volume enclosed, well, see, here's the thing. Because this changes every time I take a step, I can't just do the whole volume. I have to do this tiny sliver of the volume of radius dr. So what that means is I have to back up, and I can't do this yet. I have to look at one tiny little piece at a time. So, sorry dude, we now have to use calculus. And we can't just do total mass enclosed over total volume enclosed. We have to do tiny mass enclosed over tiny volume enclosed, and we have to look at just this ring here. We can't look at the whole thing like we did last time. We have to look at just the ring. Well, how are we going to look at just the ring? Well, we have to get the what's called the volume element. The volume element is, what's the volume of that tiny ring there? That's a derivative of the volume. So if volume is equal to 4/3 pi r cubed, if we're going to take the derivative of this with respect to the radius, so derivative of the volume, the 3 comes down, multiplies by the 1/3, the 4 survives, the pi survives, the 3 turns into a 2, and now we have a dr there. So now we've taken the derivative of the volume with respect to the radius. And if you know your formulas from geometry, you should notice that this is the surface area of a sphere. So to get the tiny volume of, that sliver of the balloon, it's the surface area of the balloon times the thickness of that balloon material. What we have here is the radius of the balloon times the surface area of the balloon, or which gives us the surface area of the balloon, and then times that thickness of the balloon gets us the volume of just that sliver there. The surface area times thickness, this is sort of like finding the volume of a sheet of paper. You can find the volume of a sheet of paper by saying length times width times thickness. Well, length times width, that's the area of a sheet of paper. And then that thickness would be like this dr here. So now we can take this and we can figure out what the mass enclosed is going to be. It's going to be rho, which is kr squared. And now it's going to be this expression for the volume. 4 pi r squared dr. And now we can figure out how much mass is going to be included in there. And we're going to do that on the next board because I have some calculus to do. And I want to make sure I have enough space. So derive an expression for the mass enclosed by an imaginary sphere of radius r. So what I want to know is what's the total amount of mass that I've enclosed by the time I get out to here. In order to do that, I have to add up all of the little tiny shells all along the way. Think of, the Russian doll set, the nesting dolls, where you have, the guy on the outside is painted as like the king, and then you take him apart. Inside, you've got the queen, and then you take her apart. And inside, you've got the prince. You take him apart, and inside, you've got the princess. You take her apart, and inside, you've got the baby. So inside the nesting dolls, and each one is made of wood of the same thickness, but every time you take one off, you've got something inside. So same deal here. We're going to add it up. So this guy, and then this ring, and then this ring, and then this ring, all the way out to however far I want to go. And we're going to start here. The total mass enclosed of just that ring is going to be the density at that position times the volume, the surface area times the thickness of at that position, and we're going to add them all up by doing calculus to it. So what we're going to need to do is put our summation symbols there. So let's rewrite this over here. We're going to do mass enclosed, and we're going to go from 0 to however much mass I'm going to enclose, because when I'm at the very center, I've enclosed no mass. This is like having the balloon not blown up yet. There's no air in the balloon yet, so it hasn't enclosed any space at all. So we haven't started to blow up our imaginary balloon. We haven't enclosed any mass. And we're going to go from the center of the planet, where the radius of the balloon is 0, all the way out to whatever radius r we want to go to. Now, later on, we're going to want to enclose everything, so we're going to go out, we're going to replace this little r with the big R for the radius of the planet later on. And this guy will be k r squared, 4 pi r squared dr. And you can see here that we need to have that dr to tell us that r is the variable and not k. Because without that, we wouldn't know for sure what is the thing that we're measuring here or calculating. Let's clean this guy up. What you should know from calculus is that anything that is a constant gets to come out of the antiderivative. So the 4, the pi, and the k, they're all constants. They get to go along for the ride, so they come out of the integral, the antiderivative. And then we can focus on just the variable. So with this polynomial here, you increase the exponent by 1, divide by the new exponent. And on this side, we're going to get mass from 0 to mass enclosed. And over here, we're going to get 4 pi k r to the 5th over 5. And we're going to evaluate it from 0 to r. Substituting in our limits, where we're going to have top limit minus bottom limit. We're going to end up with the mass enclosed is going to be equal to this expression. Notice how this is a little bit different from last time, where it's not simply the total mass of the planet times some ratio. And that's because we have an equation that describes how dense the planet is at any given radius. Now we can use this to derive an equation for the force of gravity between the planet and an object that's placed that distance r away from its center. And I want to do this both inside and outside the planet. Inside the planet, we're only going to have this little r here, and our expression, Fg equals minus g m enclosed, mass of the object over r squared. Now we have an expression for a mass enclosed. It's this guy. So we're going to replace that. G 4/5 pi k r to the 5th mass over r squared. And let's remind ourselves that that's for inside by putting F in there. 4 pi k g m over 5. And then we're going to have an r cubed there. So what this says is every single time I take one step away from the center of the planet, the force of gravity on me is going to increase according to the cube of that step. It's going to increase very, very fast. This should make intuitive sense because the density is increasing very, very fast. We're going from a very not dense planet, it's almost a hollow planet, to an extraordinarily dense planet around the outside. This is almost the shell of a planet, where all of the mass is on the outside and there's very little inside because of the fact that this is a squared function here. Now outside, here's the thing about outside. Outside, once we get to the surface of the planet, this stops at big R and it stops increasing. That just becomes a number because the planet has a defined size. So F out is, oh, and I dropped my minus sign there, so we should have a minus there. Minus G, mass enclosed, mass of the object, R squared, and now minus G 4/5 pi k big R to the 5th mass over R squared. And if you notice, everything on the top here is now a number. It's a constant because that's no longer a variable. Once you reach the surface of the planet, there's no more planet to enclose, so you have to stop enclosing more planet because now it's empty space. So once you reach the radius of the planet, this is now just a number. And if we clean this up so that it looks a lot like that one, makes it easier to compare. We're going to have a minus, we're going to have a 4, a pi, a k, an m. Oh, I dropped the g. The g, an m. Now we have an r to the 5th, and we are dividing by 5, and then we have a 1 over r squared. And if you notice, as soon as you get outside the planet, we're back to a 1 over r squared. It doesn't matter what's going on inside the planet as soon as you get outside the planet. Well, let's make a graph of those guys and see what that looks like. What we have here is a cubic function for inside the planet and an inverse square function for outside the planet. So what we're going to get outside the planet is the same thing that we got last time. We're going to get an inverse square relationship. And we indicate this curve is the force is related to the inverse square. Inside the planet, though, we're not going to get a line. We're going to get a cubic-y kind of thing. Where the force is going to increase very, very slowly at first, and then jump very quickly at the end as that radius has reached the maximum radius of the planet. So we're going to say force is proportional to r cubed right there. And we should probably label what this maximum value is. That is right at the surface of the planet on surface of planet. And it will be when this little r down here is the radius of the planet. It's also big R. You should notice that when we do that, this r squared becomes a big R squared, and it cancels with this guy, and we get an r cubed up here, and this whole constant out front is the same. Take a look over here. This little r becomes big R cubed, and this constant outside is the same. At the surface of the planet, these two guys are equal. So these guys are equal at surface of planet. I suppose it is possible that there is a planet for which, when you jump from the inside to the outside, there's a discontinuity and they are not equal. We're not going to deal with that in this class. That's more of a situation that you would run into with electricity, where you have a charge on the inside of some kind of metal dome and a different charge on the outside of the metal dome. And when you pass through the metal dome, let's say you're the size of a proton, and you pass through that metal dome, you're going to see a discontinuity in the electric field. That will be relevant there. We're not going to deal with that situation here in gravity. And what we get for this maximum value is 4 pi k g. And if I only want gravity, then what I've done is I've divided out the mass of whatever the object is. And I've said, well, the object doesn't matter. What I care about is the planet. So we're not going to include that m there. Big R cubed over 5. And because this is attractive, we will have a negative sign there. Now you have to be careful, because if they ask you for the magnitude, and I didn't include the word magnitude here, but if I had included the word magnitude, we would have to get rid of that negative, because magnitude by definition is going to be positive. Now, how else could I change this sort of situation? At this point, the main way that I could change this situation is by changing my starting equation there. I could say, well, what if it's not a kr squared? What if it's just kr? Or what if it's k over r? What if it's most dense at the center of the planet and it's least dense at the rim of the planet? That is roughly how our gas giants work. Our gas giants have a very dense core and then a gaseous atmosphere that extends for most of the volume of the planet, as opposed to the Earth, which is mostly rocky and then has a tiny sliver of atmosphere. So for a gas giant, it would be a very dense core that then drops off and basically doesn't exist by the time you get to the outer edge of the planet. That would be a density which is k over r, or perhaps a k over r squared. All the rest of this math would remain the same. You would just change this function right there, and that would affect your polynomial by the time you get to this step right here. But that will be an issue for you to deal with in the homework.